So now we want to get our hands dirty and we want to dig deeper and look at that precise epsilon delta definition of a limit. And in doing so, we want to look at the following problem. When demonstrating that the limit as x goes to 3 of the function negative 2x plus 11 is 5, with epsilon equal to 0.4, which of the following delta values suffices? Delta equal 0.4, delta equals 0.2, delta equals 0.24, delta equals 0.02, or delta equals 0.04. There may be more than one choice, and we'll select all the deltas that apply. So where to begin? Well, I'm actually a visual person, so I always like to start with a picture to kind of see what's happening in this problem. So let me draw an XY graph. And then on that XY graph, let's go ahead and let's actually graph that function. My function is y equal negative 2x plus 11. And what is that? That's a line, and that passes through 11 on the y-axis and has a slope of negative 2. So for every 1 unit we move to the right, we move 2 units down. And so that actually puts me right here at a nice line that comes down. So now specifically, we want to pay attention to where we're taking our limit. We're taking our limit as x goes to 3. So I want to zone in on x equal 3 down on the x-axis. And sure enough, if I was to map where x equals 3 hits the function, I would find that it hits at 5. And so that statement that the limit as x goes to 3 of negative 2x plus 11 equals 5 makes sense in my picture. Our next step is to incorporate this epsilon. So we're given that epsilon is 0.4. And what is epsilon? Recall, epsilon is just a number, and it's going to represent a distance on the y-axis when it comes to this delta epsilon proof. So along the y-axis, we're going to take an epsilon value of 0.4, and we're going to create a band. We're going to go 0.4 units up above 5, and we're going to take 0.4 units below 5. So we're going to have right here 5 plus 0.4, which is giving me 5.4. And down here, we're going to go down 0.4 units from 5. So that's going to give us 4.6, which is 5 minus 0.4. Once we have our epsilon band, we're good to go. Because remember, this epsilon band is applied to the function, and so we can find x values mapping to those particular y values, 5.4 and 4.6. So if I come down, I will find 2 x values that map to those y values. Now the question is, what are those x values? And then once I get those 2 x values, what is the distance between those x values and the value 3? Because that's going to be representative of our delta. So let's calculate those x values. When y is 5.4, so let's look at that upper level, that upper band. When y is 5.4, what is the corresponding x value? So we take 5.4 minus 11, and we're going to divide by 2. Negative 2. 5.4 minus 11 is negative 5.6. Dividing by negative 2 on both sides gives us that x is 2.8. So our x value corresponding to the y value of 5.4 is actually just 2.8, okay? That's this value right here, which when I map up is going to go to the y value 5.4. Now I'm going to repeat the same process on the other side and find the x value that pertains to 4.6. Now, because we have a straight line, it should be pretty constant, so we should be having a similar delta on the right side, but let's check and see. We plug in 4.6 in place of y, right? Because it's the y value. And the x value that corresponds to that y value is simply 4.6 minus 11, and then we'll divide by negative 2. 4.6 minus 11 is negative 6.4, and dividing by negative 2 gives us negative 3, negative divided by negative is positive, so positive 3.2. That makes sense in my picture because sure enough here, see, there's my 3.2. That's my x value on the x-axis that pertains to this lower bound over here, 4.6, on the y-axis. And so everything's coming together. Our last step then is to calculate the delta. And remember, the delta is just that value along the x-axis. So it's the distance, it's that distance along the x-axis such that every value within a delta band around 3 will map within this epsilon band up here. And so we can use these two guiding numbers, 2.8 and 3.2, to kind of help us. If I look at the distance between 3 and 2.8, so if I want to look at that distance between those two values, that's actually equal to 0.2. And if I look at the distance between 3.2 and 3, that's also equal to 0.2. In fact, along this x-axis, if I have delta equal to 0.2, then every x value will be in between 2.8 and 3.2 and will correspondingly map up here to the epsilon band where epsilon is 0.4. So it looks to me that as long as delta is 0.2 or any number smaller, because if you pick any delta smaller, you'll still fall in that epsilon band. So as long as delta is 0.2 or anything smaller, I will satisfy the precise definition of the delta epsilon limit, with this epsilon equal to 0.4. So we look at our list, and we look for all the values that are equal to 0.2 or smaller. So delta equals 0.2 works, not 0.24, 0.02 is smaller, and delta equals 0.04. Those three delta values are all less than or equal to 0.2, and thus will satisfy our definition.